who has, by the looks of things, nicked somebody else's acronym and the name of somebody else's model. So we'll see how he justifies that in the next hour.
Okay, thanks for that introduction. So I will talk to you about the some work we're doing on non-hydrostatic atmospheric modeling. I should thank our sponsors, the National Science Foundation, the Office of Naval Research, and the Air Force Office of Scientific Research. I am at the Naval Postgraduate School in Monterey, California. So let me just give you some background about the motivation for the work we're trying to do. So currently in the US, there's a movement to construct a one NWP model. We're trying to get with the times and trying to pool our resources in some sense. We have way too many models. Not that I'm complaining about that, but so the idea is to try to see if there's any kinds of models that we can pool together for different agencies. And from that point of view, the models are required to be highly scalable. And the idea is to have a model that is valid at the mesoscale. Something happened to my slide here. And the idea really is applicable to medium-range numerical weather prediction and decadal timescales. So one of the comments you hear is something like, from 30 seconds to 30 days is what the model should be used for. And from that point of view, what we're trying to do in my group at NPS really is to develop some sort of framework, and I'll talk to you more about this in a minute. And the idea is we're trying to test a lot of different ideas. And the easiest way for us to do that is to put it into one system to be able to do these things. And the goal that we have is to develop, to have flexibility in the class of numerical methods that we use. For example, we have a set of element-based Galerkin methods. I'll talk more about that in a minute. We would like to construct highly scalable models on current and future architectures, and meaning that we're not just CPU-based parallelization, but also GPUs. We have started looking at adaptivity as well, statically and dynamically adaptive. And of course, with dynamically adaptive comes adaptive time stepping and this idea of multi-rate time integration. And then of course, this becomes an issue that, as David said in the beginning, this is not what we're concentrating on in this program, but this becomes a key issue. Is how do you use existing physical parameterizations when you have these adaptive methods? How do we do that effectively? And so here's the goal of my talk. The goal of my talk really is, I'm going to tell you about what we're doing in my group, but also I really want to lay out a roadmap for the work that we wish to conduct while we are here. So obviously we're open to other ideas as well, but I'm going to let you know what we think we would like to discuss here and collaborate with people here. So from that point of view, I always have to mention your collaborators. We have, let's see, how many of these, two of these guys are currently here. Michal Kopera and Andreas Mula are working on model development. Shiva just left us. He took a faculty position at the Indian Institute of Technology, and Jim left us for private industry to make much more money than I can ever pay him. We also have people working on moist physics and turbulence models, and primarily the people at the Naval Research Lab. And Simone, who is actually here, has been working with some of these ideas with us. And then we have some people working on time integrators with us from Argonne National Lab, Emil Constantinescu, and at the University of Washington, Dale Duran. And then within my department, there's other faculty members that, is there a question? No. We have some people working on preconditioners and iterative solvers, and these are people in my department. Okay, so having said that, let me just give you a brief outline of the design philosophy of our model. We call it a unified model in the sense that we're talking about unified dynamics, meaning that we would like to have a model that can do the full non-hydrostatic equations to be able to solve regional problems as well as global problems. And the idea is that you solve the same model solves the exact same equations. And then obviously this is easier for us to do this because then we can just maintain one dynamical core and just change things like the grids, the forcing, the boundary conditions, etc., to be able to have one model that does all these things. And of course, unified numerics is easy for us in some sense to do if we think about developing a model that has this element-based Galerkin machinery. And we saw Matthew talk about CG and DG methods, and that's basically what we do. So we have a CG method that in the model, this tends to be a little bit more efficient for low processor counts. The DG model, it really, really shines at high processor counts. And both of these, the CG and DG methods, uses the exact same mathematical arsenal. I'll tell you how we combine that in our code. It's very easy to have both in the same code. And you can choose whether you want to do CG or DG within the code. Unified code, we have a suite of time integrators, explicit and implicit explicit methods. We also have a whole bunch of iterative solvers, including GMRes, BiCG-Stab, Chebyshev. And then we have a whole suite of preconditioners to do our IMEX problem. A lot of them are the ones that you see in the book by Sod and other people. But we also have our tailor-made preconditions that we actually have worked on. And this is kind of, we're pretty happy with the results we're getting with these preconditioners. One of the things that I like to do while we're here is to see if people here who have a need for preconditioning, will these preconditions work for you? I'm hoping to do that. We think it should work for any problem, but I like to put it to the test, really put it to the test. And finally, unstructured and adaptive grids, our models can handle that. We just started looking at non-conforming AMR. We don't have the capability to do conforming AMR yet. I don't see it as a problem. We haven't developed the technology to do that offline. So meaning, we'll talk more, I'll bring this up more in a minute, but the point is that with non-conforming AMR, I'm gonna jump the gun. Let me just hold off on that. I have a whole bunch of slides on that. Okay, so unified dynamics. Here's my talk summary. I want to tell you what I mean by unified dynamics, where we are and where we think we'd like to go. And I'll do this for all these topics here. Unified dynamics. So currently, we solve the fully 3D compressible equations. And the idea that the applications we've tried so far are cloud resolving, mesoscale, and global scales. And these are very idealized test cases. There's no physics in the model, not the one that I'm showing today. The equations that we solve are the conservative form of the Euler equations. We use a density, so it's conservation of mass, momentum. Here's a proxy for energy, so theta, capital theta is rho theta. And then we have an equation of state to close the system. One of the things that we require, because we want to be able to solve the same model to do mesoscale and global modeling, we need our equations to understand that. So what I mean by that is if you try to write your variables in some split form, right? So here the variables with a 0 subscript is some reference field, right? Let's say it's hydrostatic balance reference field. Well, you can see that we have them all in terms of x, y, and z, because typically if you're thinking about just something on the plane, and say you have a mesoscale model that you only have x and y direction, and you're worried about the balance only in the z direction. Obviously, you don't need x and y here. But if you're on a sphere and you're using Cartesian coordinates the way we do, we have to have these reference fields represent the entire x, y, z space. And these are the perturbation variables that we solve for. Okay.
Go back one slide, well, no, two slides.
Yeah. Yeah?
Yeah.
Okay.
Frank?
Yes, question.
You don't have a t in the reference state? Are you?
That's correct. It doesn't change the time.
So you're ruling out something like Laplace, where you'd have a reference hydrostatic, which varies in time, and a.
You could. We haven't done that. I mean, that would be interesting to talk about. Well, I'd be interested in hearing what your take on that is. Not right now, but some other time. Yeah. Okay. Are you going to talk about it in your talk?
No.
Okay. And so then what happens is to be able to have the set of equations that can handle mesoscale or global in these Cartesian coordinates, it turns out that what happens when you go through the math, you end up getting your hydrostatic balance look something like this. And then you have something, if you wanted, for example, to have, so here's now if you have something a little more interesting, if you're trying to get some kind of geostructural balance or something like that. But in the end, what happens when you plug this stuff to the original equations, you get a form that looks like this. And it doesn't look very different from the original equations, except I want to draw your attention to this operator H. This H here, it's just some matrix. It ends up being just a projection matrix that allows you to define hydrostatic balance, for example, or other such balances. So that's really it. And once you have that, now you can solve your problem on either Cartesian geometry in a mesoscale sense or on the sphere. So here's an example of a test case, the 3D linear hydrostatic isolated mountain. So the grid is just some structured looking grid like that. If you look really closely at the bottom, it's some little bump, right? So this is nice because it has a lot of the features that you'd like to see in a mesoscale model. We have to give it more realistic boundary conditions. So we use absorbing boundary conditions here in the lateral boundaries on all, let's see, I guess, yeah, on all 4 sides, 5 sides, and then the bottom is in the flux here. And then you have an inflow boundary condition of 20 meters per second, et cetera. And then if you do this and you run the model, you have some analytic solutions, especially along the surface of the mountain. And you can see here, in fact, the colored solid lines are our solutions. There's some dotted lines in there that are the actual analytic solutions. You can't see them. I don't know why you can't. I can see them better on my screen. There is a difference, but you can't see them that clearly on the projection. Actually, maybe here you should probably see a little bit of it there. So there's some difference, but all in all, pretty good. And then if you look at so here we've compared the CG, DG, and analytic solutions. The analytic solution is, again, it's not shown there, but they are on top of each other. That's the good news. And then you do this for the U velocity and the V velocity, and things look pretty good. We also have run an inertial gravity wave on the sphere. This is after 48 hours, and this is just a slice in the Z direction along the longitude here. And the grid looks something like this. It's a hexahedral grid. It's a cube sphere grid. And if you do this, you find that the theory tells you that it should be about the velocity, the gravity wave velocity, 32 meters per second. We get NUMA gives us about 33. And then just for comparison, we got this out from a paper by the people who, Sato and, I'm drawing a blank on his name now.
Tomita?
Say again?
Tomita?
Tomita, thank you, Tomita, yeah. Hirofumi Tomita, right, thank you. Yeah, so a paper from them. So that's why we show the NICM result here. That's the only reason why we do that. Anyway, all in all, pretty good agreement. One of the things that we see that we would like to do with this unified dynamics is, as I said, we solve the fully compressible equations. Obviously, you have to deal with acoustic modes. Is there a better way? Is there a better way to do this? People have looked at other equations and elastic and pseudo-compressible sets. It would be nice to do, I mean, I know people have been doing this, but we'd like to do it within our framework. Can we do this comparison and see, what are the pros and cons of doing fully compressible versus the inelastic? We've developed a lot of technology to solve large systems of equations. I think that doing the inelastic won't be that much of a problem for us, but we would just like to have a rigorous test, at least within our setting, using CG and DG methods. Okay, unified numerics. I'll tell you where we are, what we've done with these. So really what I want to talk about is these element-based Galerkin methods. We've heard already from Jürgen about continuous Galerkin as well. We heard from Matthew. And we also want to talk about discontinuous Galerkin and then this unified CG-DG representation. And for those of you who, I'm sure everyone here has seen these before, but just to make sure that there are no holes, I want to talk to you about how these element-based Galerkin methods actually work. So let's say you have this grid of 4x4 elements. And if we look at just one of these elements, right, you can imagine having these interpolation points inside that element. So here we have a cubic polynomial going through here. So you have 4x4 internal grid points in your element. And that's what you use to construct your higher basis function. So for example, if you look at the Lagrange polynomials, you don't have to use Lagrange polynomials, and they tend to be the polynomial of choice. So the basis function associated with that grid point there looks something like this. So the typical Lagrange polynomial has their cardinal functions. They're 1 at the grid points and 0 everywhere else, but they vary between the points, right? Meaning this, if you look at this point here, it's going to be 0 at all the other red points, but between you see there's actual variation, right? And so here's, for this point here, for example, that's what the basis function looks like. So for that point, the value is 1 here, and all other red points is 0. So you get the idea. That's the general idea of these Lagrange polynomials. And the way you actually solve the problem is you write your equations. We write them in conservation form. And then what you do is you say, since Q is my solution variable that I want to solve for, I want to approximate in some sense by some basis function expansion. once I do this, then I can bring this into my flux tensor and my source functions as well in the following way. And then I plug these approximations into my original PDE, okay? And then now, one of the things that I want to draw your attention to is the fact that you want to do this interpolation means that if I'm saying I want to get an nth degree approximation of Q, I need a polynomial interpolation that is least of order n. Then when I plug this into my continuous PDE, if I looked at this continuous PDE and I brought the right-hand side over here, I should get this guy plus that guy equals minus S of Q equals 0. I don't get that. I get a residual because I'm using a finite dimensional expansion here. And then the name of the game is to try to multiply by test function, integrate, and drive that residual down to 0. Okay? And the way we do that is you then seek for example, a basis function and a solution that lives in some space. I give you the gory details here. But the bottom line is that this basis function and the solution variable live in some H1 and L2 space. And really the thing to really point out is the fact that they're nth degree polynomials. And then once I multiply by test function and integrate within my element, each one of my control volumes or elements, I then can derive that to 0. And it really is, it's the same argument you have in least squares. That's exactly the same argument you have here. That error is minimized when the basis function and the error are orthogonal. Question?
So what kind of a space finally you get? A combination of two different basis function.
Okay, well, so here's what I mean. So in the case of CG, you're looking for the basis function in one space. In the case of DG, you're looking for it in a different space. So my point is this: at this point, before I get to this line here, and actually even if you ignore this statement here, right? If you just look at this statement here and this entire slide here, I haven't told you which method I'm using. It could be CG or DG. It doesn't matter. What makes the distinction is when I tell you which space that basis function lives.
So the convergence, the variation in convergence can be handled by this. I mean, like the one method is going to converge in a different way. Other elements are going to converge in a different way.
No. So I'm saying from the beginning here, right? I set up this formulation here, and I tell you right before my simulation, I'm either using CG or DG. That's it. I'm not using CG and DG throughout my domain.
Okay.
Is that your question?
Yeah.
Yes. No. Sorry. Yeah. So I guess the unified CG-DG could be misleading if you think that I have. No, we haven't looked at that. I'm just saying that within our code, it's the same code, same formulation, but right before the simulation in our input file, we say we either run CG or DG. Yeah, I thought about this, about how you can unify, but that's another question. I don't really know how to do that yet. Okay, so then going through the rest of the formulation. So now you have your least squares solution here, and then when you go ahead and think of every integral that you have already as an element, you end up with some matrix form that looks like this, right? And in this case here, I've done integration by parts. This is where this term and this term come from. I've done integration by parts, but it's not really necessary to talk about that now. And then you end up getting these matrices. So this M superscript E is the mass matrix inside each element, and then you have a differentiation matrix, and then you have this M here it's kind of like a mass matrix, and that's where your fluxes come in, right? So it's similar to a mass matrix, and except it's augmented by a normal vector like you would have in finite volumes when you do fluxes, etc. And so the key point here is now your integration has to be order 2n because you have at least you have 2n polynomials, right? So that's where you want your integration formulas to be. If you want it to be exact, they have to be at least of order 2n, your integration. And then here's the difference. Now, once you have all this, I still haven't told you what I'm using, right? I'm either using CG or DG. And then in the DG case, what happens is there's once you solve this problem here, right? Then you have to make a choice, and the choice is the following. If I don't tell you anything else, and I just show you this equation here, in this equation, right, the superscript e's here mean that everything lives inside of an element. So I don't know what's happening at the neighboring elements, right? That's not a well-posed problem because I have a control volume that knows nothing about neighbors, right? So the question is, how do you then gather the information to have these elements communicate with each other? Is by something that we call a communicator. Communicator is nothing more than, if you're a finite element person, it's global assembly or direct stiffness summation. That's what it is, right? So here's what, in the CG case, it's easier to think about, right? What this communicator really is nothing more than global assembly. So let's say I wrote everything in this equation here to the far right-hand side except for the mass matrix, and then I multiplied by the inverse mass matrix. Then what happens is, that's what I'm calling R here. Then R looks something like this. Say I have a solution R at these two sets of grid points at an interface of two elements, right? At this point here, when I do the step here, this element and this element know nothing about each other. And then what this does is there's a gather-scatter operation. And I'll talk about that in a minute. And in the DG case, you don't need to do anything, right? Because DG, you're just basically, all you have to do is multiply by the inverse mass matrix, because everything is being handled by this term here. This term here is a flux term that tells you that you're basically at an interface and you're solving a Riemann problem. Oops. Okay. Now in the CG case, you'll see what's going to happen. I'm going to do a gather operation to make sure that these guys are C0 continuous there. So I do something like this. Now the solution is continuous here. It took information from the two neighbors, and then it's going to. So that's what the G is. It's a gather, and then it's going to scatter it back. There it is. So that's what CG did, right? All CG did is it had a DG solution and it did gather scatter. Okay, and then if you look at convergence rates for CG and DG, this is for a 1D wave equation after one revolution. You can actually see that if you compare it numerically versus the theoretical rates of convergence, you see that you get essentially the same kinds of rates. So here, for example, I'm using an 8th order polynomial, and you see that this is the theoretical 9th order accuracy, and you get the same kinds of rates. Okay, unified numerics, pros and cons of these methods. So in red are the things that I consider a disadvantage. In black it is what it is. And in terms of CG, what you see is that, well, the methods are very similar, right? Really the only difference is that in CG, you really require inexact integration, because that way, what I mean by that is, the name of the game in CG is you want a diagonal mass matrix. You want to get away from having a mass matrix, right? Because like Jürgen talked about, if you have a mass matrix to invert, that's going to kill you. No matter how great the method is, that's going to kill you. So in CG, we tend to get away with that by living in higher order polynomial spaces beyond 4, and we use inexact integration, and everything's fine. In CG, we tend to use only tensor product basis functions because we can get away with having an exact integration. If you do stuff on triangles, there's no set of points that give you good interpolation, good integration on a triangle. Mark and I worked on a paper in, what year was that, Mark? 2006, and it can't be done. Since then, we've seen that there's a proof by Boss, right? That you can't do it. There's no such points.
So
we should have waited. We should have waited. We spent a lot of time for nothing. Yeah. Not easy to use with non-conforming adaptivity, and not that it's impossible. We just haven't done it, and this is something that we'd like to talk about and do while we're here. I know other people in this room probably have worked on this for CG. Constructing positivity, I shouldn't say I didn't say it's impossible. It's not easy. Mark will probably talk about limiters for CG. And in the case of DG, it really has a lot of the same, all the good properties DG has the good properties of CG, and easy for non-conforming. In principle, it's easy to construct positivity preserving methods. It's still not trivial, but it can be done. And I would say the main drawback of DG really is this issue with constructing sure complements for IMEX methods. We haven't been able to do that. We're still working on that. We still haven't been able to do that. That's something that also we'd like to fix while we're here. Things we like to work on. I already mentioned the IMEX problem and sure complements for DG. Construction of positive definite methods for both CG and DG would be great. We've started working on this for DG. For CG, Simone has worked on VMS. These are called variation multiscale methods, which are basically a stabilization method. Matthew talked about SUPG, and it's something like that. It's just it extends that whole class of methods, of streamline upwind Petrov-Galerkin methods. And we've used these with great success in CG, and we'd like to do the same thing with DG. We need to compare these two approaches and quantify the cost-benefit analysis of actually using this stuff. So, you don't get things for free, unfortunately. You pay a price. Okay, time integration. I'll talk to you about this We've been spending a lot of time on time integration. It's one of my favorite topics. And what we have right now is we have a whole bunch of time integrators in our code, which is okay. It's nice to have them, right? But again, it's a lot of choices, and you have to decide. Okay, if you use this time integrator, which precondition are you going to use? Which iterative method works well? So we also have been building GUIs to make these choices a little easier. So basically, it's a pull-down GUI, written in Python. They kind of go through, and once you pick the time integrator and other things, it starts only giving you smaller options to what you can pick, right? Because otherwise, before it was you give the code to someone, and they would break the code, and you couldn't figure out why it didn't work, and then you're like, oh, okay, oh, you use that and this? Oh, no, I can't do that, right? So this is stuff that we've been learning when we've been handing out our codes. Let's see. So yeah, one of the things that we've done is all of our time integrators. The design principle of NUMA is every time we bring in a new time integrator, it has to go through the same calls as every other time integrator. It might sound like a bad idea, but it really allows us to build a new time integrator very easily because we just make a copy of one time integrator and then change something else, right? It's not a whole lot of work. Everything, we always know that's going through the same calls. And when I say by the same calls, I really mean anytime the spatial operators have to be used in some fashion by either CG or DG, it always goes through the same set of calls. That has allowed us to build things very quickly. So this just allows us to build, time integrators very easily. For example, we have a collection of backwards difference formulas, both explicit and implicit, a bunch of Adams methods. Leapfrog is in there, Crank-Nicholson, and we have implicit Runge-Kutta methods as well. And today I want to talk to you a little bit about time integration, but I don't want to spend time on explicit methods. Implicit methods we have not had great success with. When I say implicit methods, I mean fully implicit methods. And so most of the work that we've done is on implicit explicit methods, and I'll talk to you a little bit about multi-rate methods. So multi-step IMX methods, here's the idea, right? You've just discretized your PDE. So S is an operator that's now, it's a discrete operator, and then you have now a total derivative in time that you now have to discretize in some fashion. And then the trick to IMX methods is you basically construct this operator L, a linear operator that has all the fastest waves that you're looking for in your system. What are the things that are traveling fastest? In our case, it's acoustic waves. So we have the acoustic waves in there. And then the idea is now, once you have it broken up in this fashion here, delta is a switch. It's either 0 or 1 to give you explicit or semi-implicit or IMX. And so the curly brackets is stuff that we do explicitly, and the square brackets is stuff we do implicitly. That's why we need L to be linear. Otherwise, we have to go through a nonlinear solver, which we've been trying to avoid that. And then if you then use some kth order time integrator, we tend to use these higher order Runge-Kutta methods for the most part, but we also have BDF methods as well. And then once you do go through this discretization, what you really get is your usual linear algebra canonical problem, right? You get AX equals B, where X is your solution variable you're looking for, A is some linear system, and B is the right-hand side that you know. Then the trick is this, right? So here's where the Schur complement comes in. So if I show you the no-Schur form of the shallow water equations, you have a variable u, that's your velocity vector, and you have phi, some scalar. And then the idea to go from the no-Schur to the Schur form is you're essentially using block L decomposition. So I'm trying to zero out this block system here, right? I want to zero there. And when I do that, when I apply my L decomposition, I end up getting on this row here, I get this operator that looks something like this, where I have to worry about there's an inverse of a matrix here, right? So A11, fortunately, is a mass matrix. In our case, it's either diagonal for CG, or it's very small element-wise for DG. So that's the good news. But then once you have the system here, now this is what we solve for. So this is the Schur, this is known as the Schur complement. And one of the advantages of using the Schur complement versus the full no-Schur form, so here's where the DG thing comes in, right? DG and IMX methods. For this form here, you can use either CG or DG without any problems. If you go to this form here, we can do this for DG. For DG, for CG. For DG, it's a little more complicated because the matrix doesn't look like this. It's a little more convoluted because of the fluxes, et cetera. And actually, this is a topic that I'd love to talk to you guys about. I can give you in my office, a 15-minute presentation on this to explain to you really what is the issue. We did this at IPAM a couple of years ago, and still we've got no takers. No one's interested in this problem apparently. We're very interested in it. So one advantage of the sure form, obviously, is that it's a smaller system, right? So for example, for the shallow water equations in 2D, this no sure form is a 3n by 3n system where n is the number of unknowns. In the sure form, this system here is n by n. You solve that problem, and then you go back up. You use typical backward, your back solve and Gauss elimination, and you solve for u. So it's a much cheaper system to solve. But the other important thing is that the system is far more well conditioned. So here's an example. If you look at the eigenvalues of this system, right? Not surprising, you're going to see the eigenvalues along the imaginary axis like you would for a hyperbolic problem, and they're all right along the imaginary axis, right? But really, the thing to look at is the fact that they are the condition number k of this matrix is very large. I know people who work on incompressible Navier-Stokes think that's a very small condition number, but for us that work on compressible flows, that's a pretty big number. We'd like to see it smaller. And if you look at the condition number for this system here, that's in red, that's a lot smaller. And what that means is that if you're using an iterative solver, right, you're going to converge a lot faster. That's the bottom line.
So can I just ask an ignorant question? Is this linear part of the system changing each time, each step, or is this reference to the reference that you chose?
To the reference that I chose. So you could do that. We haven't done that, right? So, but the idea, right?
So you have to use a relatively good reference state for the system to be accurate. Is that right? If you used a terrible one, what would happen?
Well, so I guess you can think of it having, if you used your solution at your previous time step, you could do that, right? But we haven't done that. That's something that we've thought about. We just haven't done it. But that's a good idea, and that's something that I think would allow us, assuming that the change is not that large, right? We assume that you don't have to iterate so far. Question? Yes.
So are you using operator splitting here, and are you controlling your splitting error when you do your IMEX scheme?
Operator splitting in what sense?
Well, you're solving one thing implicitly and one thing explicitly, and typically when I've seen that, what you do is an operator splitting between those two operators.
Yeah. So you're gonna incur some kind of error on the implicit part, right? And that error is on the order of whatever your time integration method is. So and that's one of the reasons why we've gone to higher order in time. So we have a paper on this where we show that we get a lot better solution by going higher in time. Yes, you will incur that. That's true. David?
If you use P1D GP2 or another similar member of that family, and your momentum advection is explicit, which I guess it can be. In this
Your
context.
momentum equation.
Momentum advection is explicit.
Yeah,
I guess it can be.
that's right.
Then I think this falls out even for a somewhat DG scheme, because A11 is just a mass matrix in that case.
No, I'll show it to you. No,
Okay.
I don't see it unless you know something I don't know. Yeah, I'd be interested to hear about it. Yeah, because you're still going to have other terms, right? I mean, I guess that's well,
what other terms turn up in that box?
in the momentum. Well, you
I want
have
to discuss
pressure.
that with you too.
No, the pressure is the other equation, right? So no, you don't have pressure in there.
In momentum, I have pressure. What
Yeah,
do you
but
mean?
not in that block. That's the momentum coupling block.
Okay, so this is for shallow water. I show you the shallow water example. It's
Yeah,
easier.
even for shallow water, the A11 has no pressure in it.
No. I agree with you. That's just a mass matrix. But in the DG case, it's not this. It's something else. It doesn't look like that.
As a flux term.
You have a flux terms, yeah. A11, if you wanted lump flux in there, then A11 is not a mass matrix.
Yeah,
it's something else.
So that's the trick with having a continuous pressure, is if
Right.
you integrate by parts in the right way, you don't have any explicit flux terms in your mass matrix, and then this drops out even for a
Well,
partially DG
okay,
system.
that I believe. That I buy. Yeah, there was another question. Yeah, Hillary.
Does the phi include temperature or potential temperature as well as pressure?
So in this case here, just to make it easier, I just use this as water height for shallow water, right? But in the full 3D equations, right, I have terms for density, momentum, and potential temperature. Is there something else to the question?
I guess I should wait and see
Okay.
what the rest of the talk.
Well, maybe I won't address your question here. I hope I do. Anyway, so that's really the main thing. And so it turns out that one of the reasons why I'm showing you where the orientation of these eigenvalues is because we actually initially when we first started working on this, right, we noticed something very interesting about GMRes. Maybe people know this already, but there's certain kind of iterative solvers like Krylov, subspace methods, that really want the eigenvalues along the horizontal axis. They don't do very well in this case. So the first thing we did, we said we want to deal with eigenvalues along the horizontal axis, and then we found that we could construct preconditioners that just move them over there, so then we're okay now. So and I'll talk to you about that hopefully. We have some examples. This is just it's nothing more than a pretty picture. This is a density current in 3D. We're looking at the back side, so it's coming towards us. So it's like the classical density current in 2D, except it's instead of being just a, it's actually a blob. It's a blob, a 3D blob. And if you look at that, this is the time integrators we actually have been working on. We have a whole bunch of these. So this comes right out of a paper that we have. And one of the things you see is that, so you see faintly in these dotted lines are the actual theoretical convergence rates that you would get in time. And you have these fourth order, what we call, well, they're known as, by paper by Kennedy and Carpenter, as additive RK methods. They're nothing more than IMX RK methods. And you see that we have two kinds of IMX methods. One that decouples a problem that you're only solving the IMX problem in the vertical direction, or one that solves in the full 3D problem. And you see that they both, whether it's the 1D version of the 3D version, they give us the same rates convergence. And then we actually show the L2 error versus walk clock time. And one of the things that we started seeing is that if you're looking for really high order accuracy, the high order methods really do very well. The high order integration methods. Here's an example of an acoustic wave. So again, we use NICM only because we grabbed this test case from the Tomita Sato paper, and so we show theoretically for the thermodynamic variables we chose, it should be 347 meters per second the speed of sound, and we get 347. That's all that is. And if you look at the convergence rates, again in time, you actually see that you get the same expected convergence rates that you would expect. Now, this is interesting. For the global problem, one of the things that you see is that for certain levels of accuracy, the RK35 is actually our explicit workhorse method. So that one really wins for a long, long time. And then once you're looking for really high resolution results is when the IMX methods really start winning out. So you don't always see the gain when using IMX methods, depending on the problem. Okay. Work to be done on time integrators. So there's a lot of work to be done. One of the things that we're really interested in is this workshop is on adaptive multiscale methods, is on what kind of time integrators really work best for adaptive methods. And we have adaptive time stepping in our codes, but that's not all of it, right? Because so what happens is IMX will not offset the cost of small elements that dominate a time step in your simulation if you have an dynamically adaptive grid. So one thing that we actually have been working on, and I have a master's thesis student just finished, is on multi-rate methods. And here's the idea of multi-rate methods, right? So this is an XT diagram. Here's X, here's T. And say you have elements here that have a delta X spacing here, and then you have smaller delta X 1/2 over here, right? And the idea is that, say because of your CFL number, you can go from your Courant number, CFL condition, you can go from here to here to here. Whereas since you have smaller elements here, you really need a time step that's half the size, right? So the idea of multi-rate methods really is to say, how do I decouple the problem and have every element use its own local time step and then synchronize it in some fashion, in some rigorous fashion, to make sure that you indeed recover whatever the accuracy that you're looking for is. You can do that if you're not worried about rigorous, order delta t to the k convergence. But if you want to do it right, it's not trivial. And so my master's student did a nice job, but it's a very convoluted code. It's not so easy. And I was going to use one of his slides, but I'd be here for 15 minutes trying to explain it. It's not trivial. And this, of course, we're not the only ones working on this. A lot of work has been done on this, but I have yet to see these methods really be used in an operational code in some sense. Okay. Iterative solvers and preconditioners. I'm not sure how much you guys are interested in this, but I can tell you briefly what we're doing. I already told you that we have a whole bunch of different kinds of solvers. And the reason why we did this is because in one of the papers that we had on preconditioners, one of the reviewers said to us, well, okay, you've based all your preconditioners on GMRes. What about on other iterative solvers, how would they work there? So then we started adding more of them, and so we just kept them in there. But we tend to use GMRes, that's our workhorse. And preconditioning is where we've been doing a lot of, spending a lot of our attention on. And there's a lot of methods that work really well, like ILU, but they don't really scale. So that's, for us, it's really, if it's a method that works great in serial and doesn't work well in parallel, we won't look at it, right? Because that's where we have to scale well. That's one of the things that one of our guiding principles. And so instead what we've done is we found out that if we tailor our preconditions specifically to our problem, we've done very well. And two approaches are these element-based spectral optimized preconditioners, and also what we call a polynomial-based nonlinear optimized preconditioner. So this is let's assume we're solving the 2D Euler equations, and we want to use a Schur complement form. Then what happens is the goal is to accelerate the iterative solution of Ax equals b, constructing a new matrix K that makes the condition number smaller. And so here what happens is, here's a sparsity pattern of our preconditioning matrix, for example, and here's the matrix A that we're actually solving. So one of the things that we've done is, well, I'll tell you as we get around here. We use the same kind of machinery to construct our preconditioners that we use to do the global assembly in our matrix A. So here's the example. Say you're trying to solve this 1, 2, 3, 4, 5 by 5 system, and then one of the ideas of this element-based problem is that if you have bounding conditions, right, say along the top here and the bottom here, well, you have to build small matrices inside each element that has somehow, these guys approximate the inverse of A in some fashion. That's the goal. We're trying to approximate the inverse of A in some fashion, right? Because obviously, if K is the inverse of A, then you have the identity matrix here, and then everything's nice and easy. You've solved the problem. So this idea works really well, but the problem is that if you solve your preconditioners, you store them, and then you change the problem size, you change the boundary condition, you have to go through that whole machinery all over again. It's kind of pricey. It's a lot of work to be done. And then the idea is, once, say for example, in this example here, I have 3 elements that I can use that. 3 different kinds of elements. So this KC is a corner element. This is a side element. And here's an interior element. So these guys are all the same. The greens are all the same. So this comes down to having to construct 3 element matrices. And then you minimize the problem by saying that I want the spectral radius. In other words, you're trying to say that the eigenvalues of Ka are similar to the eigenvalues of the identity matrix. So you're trying to construct K that's similar to A inverse. Yeah, so, and then this is more details that you don't really need to know about. We have a lot of, like I said, we have a lot of choices for preconditioning. But the idea is the following, right? The idea is that this is the unit circle, and we basically are trying to push all the eigenvalues inside here so that we can solve the problem quickly. And one of the things that I want to talk to you about is just, I'll show you the results in a minute. Here's the bottom line. If you, on this axis is the wall clock time in seconds, right, times 100. And this is the Courant number. So one of the things that we've done is if you keep pushing the time step, right, that's the Courant number is basically a proxy for time step. You actually see that if you have no preconditioning, right, you have a small time step, you bring down the time step, I guess this one here, you get more efficiency, and then you keep increasing the time step, boom, right? The number of GMRes iterations goes to the roof, and the problem, GMRes, the cost is going to be it's a quadratic with the number of iterations. In the case of this preconditioning, you actually see that you actually start driving down the time, and I mean here you're not getting great speed up here, but the point is that you don't see this issue of the wall clock time actually going up. We compare it to other kinds of preconditioners like Chebyshev, first order and second order, and we get good results. Okay, so that's enough of this, and so this is a paper that actually appeared in SciAm, Journal of Scientific Computing. Another one we have, this is the one that we really are keen on. The idea is, what happened here? Yeah, so this one you actually see the difference. So here's the average number of iterations, right? If you have no preconditioning, boom, it just goes to the roof with time step, right? And then you see that with these guys here, with the new preconditioners, the time step is going, the number of iterations is going up with time step. But you can see that as we increase the polynomial order of our preconditioners, it's starting to, that slope is getting smaller and smaller. And here's really what you want to see is the wall clock time. The wall clock time actually is really good. One of the things, now you can see that it's kind of flattening out here. So there's going to be a sweet spot for which, what the order of that precondition should be. But the nice thing about this problem here is that this guy can be done on the fly. It's not, the previous one I showed you there's a lot of nonlinear optimization that we have to do. This one we do on the fly, and we actually use that in our 3D codes. We've used it with our adaptive mesh refinement codes, where when the actual problem changes, you got to change the preconditioners, and this works really, really well. So this is a paper.
Right, just to make sure I understand what's
Yeah.
going on here. So you're using this preconditioner on the linear part of your system?
Correct.
Okay.
Yeah.
So what is the linear part of the system in this test problem? Is this the acoustic wave?
That's right.
So the current number here is based on the speed of the acoustic mode.
Yes, correct. Yes, that's right. That's right. Yeah, and it turns out that I lost my thought here. Yeah, but it'll come back to me.
Sorry.
Sorry, having a senior moment. So, question? Yes, Sean.
In your preconditioners or your linear system, you don't seem to be worrying too much about the symmetry of the system. You start with a positive definite symmetric system or something like that,
Right.
or similar to that. But you're using decomposition method that do not worry about keeping this symmetry.
Why do you say that? I don't understand.
Well, GMRS, for instance.
Oh, well, but I guess, well, I don't see the problem. So tell me your problem. Tell me your issue with it.
Well, in my long experience, I have methods that preserve the symmetry. First of all, you could use cheaper methods like the preconditioned conjugate gradient
Sure.
rather than GMRS.
Sure.
They are more or less the same family. And they would converge better, I would think.
Well, so you have a symmetric matrix in your problem?
Always taking care of, always reducing the system to a symmetric problem.
Okay. Well, I'd like to talk to you about it. Our matrices, they're non-symmetric. We have non-symmetric matrices. Yeah. But having said that, I guess, so now it reminded me what I wanted to say to Todd, is that all of these preconditions, the way they're built, actually, it's on your matrix A. You feed it the matrix, right? Well, you never build the matrix. You have your, whatever the operators are, they're building the matrix A. And based on that, we basically use, we construct a Hessenberg matrix that's small, right? So it's basically, it really is, it's a numerical approximation of your matrix A. So whatever A is, whether it's symmetric or not symmetric, you're going to get out a small version of the same matrix that has the same properties. And the whole trick with preconditioning really is to try to come up with the convex hull of your eigenvalues. And this does it very well. So that's that's why I'm really keen on this idea, is because I don't have to know anything about your system. If I give you if you know how to build the action of A on X, and you have that in your system, we can call that, and the rest of our machinery will take care of that. We'll build the exact coefficients of your polynomial to be able to build this precondition. So it should be general, but we've only tested in our systems, right? We've tested in CG and DG, but that's all I know. It works, and it works well.
So is this built into any of the widespread linear algebra backend libraries? Because that would be an easy way that we could test it. If it was in Betsy or Trillemus or...
So yeah, so we do have, we work with people who work on PET-C. So some of the time integrators that we've developed here have gone to PET-C. The next phase is to put in these preconditions in PET-C, and that would be great. Because we actually interface also our codes with PET-C. So that's how this thing came about. Yeah, no, I agree, that's the easiest way. Okay, so real quick, because I'm going to run out of time here, is so this EBSO works great, and unfortunately this paper is just, it just got published, and then about a couple months later we came up with this idea. So now this one kind of, so don't read this paper, just go straight to this one. And then my colleague just informed me that there's a new version of this that works better, which we have nothing written on, unfortunately. So I'll keep you posted on that. So this method we really like. It's just it's really easy to solve. Like I said, we've tested it in our AMR codes, and it works wonderfully. So far, so good. And we use it for both CG and DJ, and it really is our workhorse. It's what we have in the codes. We'd be interested in seeing if this would work for anyone else. I'm curious. Okay, grid generation, real quick. Okay, so multiscale models need to use general grid generators. And of course, if you want to do variable resolution grids, you should have that capacity to do that. Your model should be able to do that. And then if you haven't written your own variable resolution grid generator, then the idea is how do you interface with other things, right? So that's a topic that I'm always interested in. Also, in addition to variable resolution, perhaps looking at dynamically and statically adaptive grids, or dynamically adaptive grids, say. So conforming adaptivity would be nice to think about. We've done some work, Andreas Müller has done some work with our DG codes on conforming, but we don't have that in our full 3D codes. We also have started working on non-conforming adaptivity. We found that this is a really easy, cheap way to do AMR. So far, so good. We like what we've seen. Okay, so if you look at a bunch of, so here's an idea. If you wanted to have if you're using a Galerkin method that doesn't care about what the grid looks like, as long as you know that you're building your basis functions on a triangle or a quadrilateral, whatever your shape is, then you can do unstructured grids fairly easily. And so here's an example. This is obviously a structured grid, but if you wanted to do, for example, a cube sphere, an icosahedral grid, or some other thing, none of these grids really, our codes don't care. As long as you read in the grid, it doesn't matter. It just reads them and knows everything's based on a certain kind of element. The only caveat here is that our codes right now are only based on hexahedra, right? Not triangular prisms, not tetrahedra, hexahedra. That's the one limitation we have. And so here is an example of what a conforming adaptive mesh refinement would look like. Say you have 4 elements and you wanted to subdivide this element into 2. We saw some of this stuff in Matthew's talk. So then if you divide this guy here, if I look at this edge here, you can see that this edge is being shared by 2 elements, and there's no problem, right? So in conforming AMR, what I say is that the conforming AMR method puts no work on the solver. Right? If you have a solver that can do any kind of regular grid, it doesn't matter, right? You're reading the grid. If you have a library that does it, then life is great. In contrast, but you have to build a conforming AMR library. That's the catch. And so here's an example of an AMR mesh refinement that Andreas did. Well, he's still working on his paper. It's in revision right now. So this is a adaptive grid. This is a uniform grid. Yeah, they're not exactly the same. You can try to get the same solution, but the question is at what cost, right? That's the question. Here, for example, is a non-conforming grid. So you have 4 elements, right? Say you want to subdivide this guy into 4. Now the issue is that this edge here, on one side, has 2 elements that own it, and on this side, there's only 1 element that owns it. So now you've put all the burden on your solver. Your solver has to understand that at some edge, there's an issue, right? So if you can resolve that, then non-conforming AMR is great, because the AMR machinery is actually very simple, right? In our case, we do things very simply. We always keep these 2-to-1 ratios, right? You divide, every time you want to just divide every element by 4, and you keep these 2-to-1 ratios. You could do more expensive things. We haven't done it just because we find that this is cheap, and it gets us where we want to go. Okay. So here's an example of results from Naval. There it is. So it's the same kind of test I just showed you. So you have, so you can see what happens, right? There's elements that have 1-to-2 ratios. And this result, so far we've been able to get fairly close comparisons between the uniform and the non-uniform. And Mihal's working on a paper on this, so unfortunately he gave it to me in Keynote, and for whatever reason I have to go through and click them one at a time in PowerPoint. So here's a uniform high resolution run. It's correct me if I'm wrong, it's this curve here, right? The green curve. So we don't show the purple curve here. So this one's the green, this one's the red, and this is the blue. And so the difference is that you're using the vertical axis here is the number of elements. So you see that the number of elements in this case is fewer than all the other runs. And here's the time of the run, right? It's not the timing, it's just the time of the simulation. So you can see that obviously you're going to get some very different results depending on how many elements you add to the phenomena. This purple curve here, we don't show it because we get the same results as this one here. It's pretty high resolution though. You can see the number of elements going up. Now, if you want to quantify benefit and cost of AMR, Then what you can see is you have the speed up here versus the threshold. The threshold is just when we do our refinement, right? So this may not mean anything to you because right now our thresholds are problem dependent. Like, we say let's once the grid feels a value of a certain number, then do the refinement. But the point is this, right? So bottom line is if you look at the L2 error, and the L2 error is computed based on our uniform grid resolution, high uniform grid resolution, what you see is that if you had a small threshold, in other words, you're refining often, you're getting 10 to the minus 6, say, whatever that means, right? You're getting some accuracy. But obviously, as you increase the threshold value, right, the speed up increases. But of course, you're paying a price on accuracy. So that's the question: is how do you resolve that? How do you measure that? And what's acceptable? We don't know. We don't know that. We'd like to look at. So we have DG AMR. We'd like to explore CG while we're here. And right now, the question is, do we go fully 3D? In other words, do we go from quads, as I showed you, to octrees? That could be too expensive, especially what do you do with the vertical column in the physics? What do you do with that? That's an issue. Right, and so the other thing that we would like to look at is refinement criteria and perform cost-benefit analysis of what works best. I'm going to run out of time here, so I think what I'll do is let me just go to high parallelization really quickly. So one of the things that you see is in the past 10 years, CPU-based computing has dominated, right? In other words, large machines like Sequoia that just went online, large Livermore. But you also see that GPU-based computers are starting to come up. Like, for example, if you look at, this is from Top 500 in June 2011, you see that only, 96.2%, so less than, 3.8% were GPU-based, say. Whereas in June 2012, now the number's starting to increase. So here's the where's the GPU machines? You can't see them here, but the market is starting to increase in machines. Oh, here, NVIDIA. These are all GPUs. So this market's starting to increase, and I think that trend is not. I've only shown you 2 sample points, but if you look at the last few years, you see that trend increasing. So the question is, do we stick to MPI, or do we have to do something like CUDA, OpenCL, or some combination thereof? I think we have no choice. We have to do that. So here's a simulation of a. I'm just showing you the simulation because that's what we use to time our codes. And what you see is that number of processes in the horizontal number. This is the speed up in the wait, what is this? Right. So that's the number of processors, and this is the speed up you're getting, right? So basically, the idea is that this means this would be 100%, right? So this black line here is ideal scaling, and up to about 32,000 processors. That's as far as we've gone so far.
What's a processor in this case?
It's a node. It's a core.
It's a core.
It's a core. And so we see ideal scaling for DG, for CG. There's a little bit of a hitch there, but otherwise pretty good. And one interesting thing that we saw, so here's now a comparison at 4th order polynomials. We do the same run up to like 16,000 cores. And what you see is that DG looks great, and there's a little issue here. And with CG, the same kind of thing. But the interesting thing is that now if you go to 8th order polynomials, you see what happens is that it turns out that you get perfect scalability. So one of the things that we've seen, and we have a whole paper that analyzes this, is Kelly and Giraldo, JCP 2012, it should be out now, that goes through this whole analysis about why that is. But the point is that higher order really buys you something. And in fact, one of the things that we see is that when you go to a higher order, say you call it 8th order higher order, even though this guy here, for the same number of grid points, the time step is small and the cost is really bigger, this one eventually wins out at high processor count because it just scales well. I mean, it's.
So have you had any problem getting your iterative solver to scale well on these machines?
So I should be specific here. This example here is explicit. Implicit is a different issue, right? We have not tested the implicit solvers to this processor count, and I suspect that we did that in the past, and we're not getting the same kind of curves. Yes. Question.
Did you normalize them, or they just happen to be exactly the same speed at 16 processors? The CG and the DG.
This is speed up, right? So they normalize by themselves.
Okay.
Yeah, we're assuming that 16 is since we don't go below that.
I got it.
Yeah.
But it's just the same DOF count between the left and the right.
Yes.
Right.
Yeah. No, that's right. So that's the good news. And then, of course, we also looked at GPU-based scalability. This will be my last slide. One of the things you see is, let's look at this line here. So one of the things that we see is that at higher, this is an 8th order polynomial. We run this on a MacBook Pro using 2 graphics cards. And one of the things that you see is that when you increase the polynomial order, you really do increase your speed up. That's not surprising. You're moving a lot of memory from the CPU to the GPU. You want to make sure that you spend a lot of time on that memory card.
Isn't that nowhere near enough threads?
Say again?
Isn't that nowhere near enough threads to
Nowhere near enough threads?
get decent occupancy on a GPU? Yeah.
I mean, it'd be nice to have more. So this is just one. So there's no MPI here. This is just CUDA
I
only.
understand that, but even inside one GPU,
Right.
so if you're on a 2050, you've got 500 processing cores, so you're undersubscribed at 500 processing cores, and actually you probably need to oversubscribe them by a factor in order to maintain occupancy on a GPU. So I would have expected to see an order of magnitude more threads than that.
Yeah, let me think about that. Think about that. Okay, so what do we need to do? So one of the things we've done is we've done a lot of stuff on MPI, and I think we understand how to do that well. With CUDA, we know how to do the volume integrals that you need in DG and CG, phase integrals that you need in DG. We started just working on this. We think we have good results, but we really need to test this. And the idea really is combining these two in some fashion. Right? That's the goal. The goal is we have CUDA and MPI in our codes, but we have not tested it on a large enough machine to be able to tell you whether this is really working as well as we expected. And particularly, we're interested in this in the AMR code. So Miha has been working on GPU for the AMR codes. That'll be a challenge. Okay, so I'm going to skip this. This is
He's out of time, and he's going to keep you from.
I'm out of time.
He's going to keep you from your beer if you keep overrunning.
Yeah. Well, here I'll just show you. Let me show you the punchline. How's that? And then I can show you the slides. Those that want to.
Can you give a short talk about this next week?
Absolutely. I'd be happy.
There we go.
So let me just go. Let me go with my concluding remarks, and it's already 4:30. One of the things that we like to do. One of the things you don't need to read this, right? One of the things that we would like to. What was I going to say? Oh yeah, that's what it was. The point of this talk, okay, was to let you know what we're doing, but it really was to kind of let you know what we've done, what we haven't done, what holes we have, and how we can, if those of you that are interested, how can we collaborate on some of this stuff? I mean, there's a lot of expertise in here that certainly we're never going to collect in our institution. So it'd be nice to hear if you guys have some ideas. I'm open to any of these topics. And so that's really the goal of my presentation. And maybe we can ask certain questions about adaptivity and multiscale. I've tried to touch on some of that. Maybe not a whole lot, but I've tried to do that in some sense. And one of the things about this code that we've been developing really is it's almost an excuse really to do science, right? We're interested in mostly, at least in my group, working on algorithms on developing these frameworks to test different ideas. Of course, in the end, my sponsors pay us to develop a code in some sense, right? But that's really not my priority. My priority really is to kind of think about, okay, well, everything that we put in our code, have we tested it rigorously? Does it really add some a benefit to what we're trying to do? So, having said that, I'll entertain more questions if you like. Yes.
Coming back to the hybrid parallelization, did you test MPI OpenMP-like parallelization?
Yeah, no, we have not done that. We kind of, that's something we ought to do, and I would imagine that's a good thing to do before we test MPI CUDA. To say, here's the baseline of what you have, and here's what CUDA is going to buy us. Yeah, that's a good idea. And that would be something that we can do fairly straightforwardly. The CUDA MPI is tricky because you have to have a certain kind of machines. In fact, we were on these NSF machines, TerraGrid, and one of the machines that we were striving to use just was decommissioned. So we're looking for a machine to run it. That's been the issue why we haven't tested is that we don't, at my institution, our machines aren't big enough to really do these tests, right? And so the machine that we're looking at, Lincoln, was disconnected, and we couldn't do our runs.
Maybe you can buy it for cheap.
Buy for cheap? Well, we need MPI and CUDA, right? It's not just CUDA's cheap. MPI
No,
getting
but
the
I mean the
clusters.
machine was the commission, so maybe you can buy it.
Or we can get that machine. Oh, we've done that in the past at my institution. I don't want to do that again.
The UK has just bought a ridiculously big GPU cluster that I don't think anyone can use. So maybe we should try and arrange some collaboration such as a UK partner, and we can get onto the new machine at the Rutherford Amberlin Laboratory and get this code.
That'd be great. Yeah, Todd.
There's a little bit of tension here in the sense that any sort of national unified model is going to have to run on hundreds of thousands of processors. But we don't have implicit methods right now that scale to that. And that 100,000 processors is going to have to be making extensive use of GPUs, which any sort of global reduction just shoots us in the head.
What do you mean by global reduction?
Well, the implicit
Oh,
method
you mean a communication?
have an all-to-one,
Yes.
which means something has to come out of the GPU, go together, come back, and then go back down to the GPU.
Right. Yeah. No. So I wish, I know Paul Fisher's should be here, and that would be a good question for him because he's had success with implicit solvers.
Okay.
So that's someone that I'm keen to talk to. Yeah, but no, you're right. That's an issue, right? Otherwise, you're gonna deal with small time steps. You know, if you can get away with it, I don't think we can in the non-hydrostatic range. I think it's
I mean,
too small.
it does cut both ways because if you have the small time steps, you don't have to communicate single numbers for global reductions over that network. You've got to communicate whole halos. So
We found much better scaling with communicating. Basically, the hardware is much better for communicating whole halos than it is doing global reductions.
Right. Oh yeah, sure. That makes sense. Yeah. Hillary.
Related question, but a lot of your results and your scaling results are based on fully explicit, not,
Fully explicit.
not heavy, not even heavy.
That's right.
Which is that, and you're saying, most of the wall clock time, the fully explicit is more efficient than
We haven't done that.
semi-implicit.
If
What about? But presumably it should all be heavy.
So that's a good question. Right. So Hillary's question is the following. If you do, the results I show on scalability is for fully explicit, right? And then I most of the results that we've said that haven't scaled well is for fully 3D IMEX. So you're solving a full 3D problem. If you do a heavy method, so you're doing implicit only in the vertical, it'll scale just like the explicit. It has to, right? The catch is your decomposition, your parallel decomposition has to be horizontal only to have everything on process in the vertical, right? To really do it well, to do it quickly. But on the other hand, you can argue that maybe that you do multi-threading or MPI or OpenMP OpenMP or CUDA in the vertical. But that will scale exactly like the explicit method.
Should scale better.
It should. Well, it'll be more efficient. Oh, and you're right. And so one of the things. Well, here, let me.
Frank, I think I'm
Should I
going to
stop?
have to kick you off.
It's only take
we can
15
continue
minutes.
this over here after we
Yeah.
let Mark have a
No worries.
Because,
Yeah, I would have actually enjoyed it.
Thank you.